work within our jobs to make that life a lot easier for us from a connectivity point of view and an Internet of Things point of view. So there's estimates of anything up to 50 billion devices that are going to be connected to the internet within the next few years. No one knows for sure exactly how many there are, but everyone's of the opinion that there's tens of billions now, 30, 20, 30, 40 billion. And it's all sorts of things, all sorts of everyday objects that are sending or receiving data from over the internet. Smart meters, fitness devices, our phones, our watches, security devices, medical devices, printers, cameras, GPSs, smart meters for electricity, stock tickers, all sorts of things. And all of these things make our life a lot easier, but it means that there's a whole lot of data being pushed around that needs to be managed, analysed and manipulated. And it's vast amounts of data. And there's a very common misconception that a traditional relational database isn't able to accommodate the amount of data that, that is used with the Internet of Things type approach, with sensory data, big data, right? The common approach that people take is to use a NoSQL database because the ingestion rate, the analysis that is required will exceed the capabilities of the database that you currently have. So what are the characteristics of these workloads? It's usually lightweight transactions. There's often complex data types, a lot of things like your Fitbit or your phone have spatial data attached to it. There's a lot of unstructured data that's coming from printers or imaging or medical devices. ACID compliance, which is the definitor for the standard transaction, atomicity, consistency, isolation, durability. It's not always required. Your business does not require all of the data that's coming in all of the time. It's nice to have, but it doesn't matter if some gets lost. And the common thing is that the data model is changing, right? There's all sorts of new devices coming in, new protocols being defined. And so, they're not standard approaches that necessarily already exist. And so this evolution is something that is viewed that a traditional relational database can't accommodate. Well, that's not necessarily true, right? Large, high ingestion workloads are not a new concept, right? We have lots of examples of customers, telcos that process, millions of call records per second. We have a whole lot of manufacturing customers or customers in the manufacturing industries who require all of their information to be streamlined and processed so that their production lines can continue to work. Stock exchanges have high volumes of data being processed every second, and it's high value data as well. And all of this is done, or we can give you examples of where the Oracle database is used to do this. And why is the Oracle database used? It's because it has been developed over many, many years and offers the capabilities to handle the requirements of the examples I've just given you. Telcos, business analysts, manufacturing, stock exchange, whatever it is that you want. And we also offer the ability to grow the database footprint as your business grows. We can scale up, we can scale out over time, right? So that you're not having to purchase new hardware because you've exceeded the capabilities of your other hardware. So let's look at a couple of examples. There's 3 examples that you can see there now. SK Telecom is one of Korea's, or is Korea's number 1 mobile operator. They process 65 billion transactions a day. They process 18, I don't know where I got 85 from, 18 terabytes of data per day. All of these customers here run on Exadata. That's because it offers them a cost-effective way to process high volumes of data, also to have the availability and redundancy characteristics that are built into the Exadata, the Exadata machine to accommodate this. The other thing that SK Telecom did is that they, in moving to Exadata hardware, they were able to compress their data from 1800 terabytes to it's around about 160 terabytes or 180 terabytes, I think, saving them a significant amount of storage that was expensive for them to maintain. They got the benefits of compression at the same time as being able to meet the volume of data that they're processing. The Department of Homeland Security in the US, we've been working with them for many years now. And they are, it says they're the world's largest law enforcement organisation. They also do all of the customs tracking across the US. So anything that comes in or out of the United States, whether it be people, cargo, shipments, is all processed by them through their centres. So they have billions of transactions a day, they have billions of queries per day, and a huge volume of data that's tracking the ingress and egress of whatever cargo, or whether that's human or physical stuff through the US. They've also had a requirement for some time to be more green. So they had to reduce their data center footprint, they had to reduce their electricity consumption, and they were also forced to slash costs because of budgetary constraints. And so by being able to consolidate and condense and have the capabilities still available to them through the Oracle database and Exadata, they can meet these requirements. And the New York Stock Exchange, like many of the large stock exchanges, does billions of transactions a day at a huge rate. So they're doing 180,000 messages per second, 30, 40, 50,000 more transactions per second. And all of it being, there's financial penalties imposed on them if they're not able to process transactions, so that they have very strict availability requirements, extremely strict availability requirements through their trading day. Now, it's not all the time, but certainly through their trading day, and that day is getting longer and the requirements are getting more for them because there's a lot of stuff that happens out of hours, whether it's reporting or whether it's still some trading. So these are real world examples of heavy ingest workloads. And I'm sure that all of you within whatever industry you're in, you can relate to some of these things. Whether it's the volume of transactions, the number of transactions that are being done, whether it's the size of the data, the database that you're trying to build, whether it's processing online all of the information that you're receiving through the Internet of Things that are connected to this. So we have examples of in many industries, all industries that would match your requirements for this. So what are the key requirements for an IoT workload? So there's scalability, flexibility, and the ability to do real-time analytics. So so we want to be able to grow our database or our environment because the number of devices is growing and the volume of data that they're collecting is growing. I think I saw some numbers the other day that the average American household has 11 connected devices within it. I don't think I have at my place, but who knows? I haven't really thought about it. We've all got phones, so so there's a few phones lying around. We've all got laptops connected to things. I don't have too many I do have a smart meter on my electricity from my electricity provider, but I don't have things like security or smart cameras or fridges or that type of thing. And the second one is flexibility. So being able to have new or different data coming in, you have to be able to accommodate that. And then the real-time analytics is being able to do analysis or analytics online at the same time as doing your OLTP transactions, so that, and without having the luxury of having ETL processes to cleanse the data for you. So let's look at scalability first. It's the ability of a system to provide throughput in proportion to and limited only by the available hardware resources. So Oracle has a couple of key features that address scalability directly. One of those is RAC. RAC has been around for a long time, Real Application Clusters. Real Application Clusters allows you to have multiple machines, multiple disparate machines connected by an interconnect, so they're able to communicate through a private, shared network, shared high-speed network, but they're all accessing the one database. And RAC provides a strong scale-out capability. So you can just add more nodes to the cluster. They can be bigger nodes, which is typical over time. The replacement machines that you would bring in would be bigger. But scaling out generally allows you to grow your environment at a lower cost than scaling up. All right. So applications can run anywhere in the RAC environment. They can run on any node. They can have pieces running on multiple nodes. And they're all sharing the same database. So we have the capability called Cache Fusion, which allows us to synchronize access to the same set of data from disparate machines. So we get parallel processing capabilities, we get scale out capabilities, we get the ability, we get availability characteristics as well. So that if there is a failure anywhere within the system, the database is still available somewhere else, and we can just fail over to those. We also get maintenance capabilities. So in the when we need to provide planned maintenance activities, we can relocate work transparent to the applications to different instances within the cluster. So we can move them without interrupting their work, and we can hide any failures from them. And as it says there, when more processing power is required, we simply add a new server to the system. Some applications will require a global scale, where it is better to break their database up into smaller databases called shards, and then use Oracle sharding to link those together. It does avoid some of the edge cases that a large single image database offers or can encounter in terms of limiting scalability or availability. Because they're separate databases, the loss of one of the shards has no impact on the others. Now, the cost of that is that your application has to understand that it's running in a sharded environment. So we have to be able to route connections around the shards, and we can do that automatically. If you've got a shard key, it makes it easier, but we can route without a key to a place where your data is served. It's easy to scale these environments. We just add another shard. Now, shards can be RAC databases as well. So an individual shard can be a RAC database. We also offer sharding within RAC. But this is a way for you to grow to a massive size. Now, it's not for everybody, but the capability is there, right? Online addition, reorganization of shards is easy. They're separate databases. Now, if you want to amalgamate data across all of the shards, there's a cost associated with that. Okay. So, as we've said, a large amount of data is coming into our database. And we need to deal with that as quickly as possible. Now, what we don't want is storage to be detrimental to the future database, future data access, right? So we have a little analogy here of going shopping, right? If you know you're going to buy a lot of groceries, would you pick up a little shopping basket, or would you select a shopping cart? Right? Shopping basket might be convenient because you've got it in your hand, but it has limited space. You know, it can be harder to unload because you've got to juggle it in your hand. And if you need another basket, well, it's not easy to get another basket. Whereas if you set out with the idea that you're going to buy a lot of groceries, then taking a shopping cart means that you have plenty of space, easy access to your items, you know, when you're checking out. Now, we'll come back to this analogy a little bit later on, but what does that mean in terms of how we're going to configure our database for scalability? So one of the things that, that we've offered for some time is big file table spaces. So big file table spaces are designed to allow you to handle large volumes of data. So it reduces, the files are larger than normal, than what was offered originally. So we reduce the number of data files that need to be managed. And when they're created, they're fully formatted. Now, there's a few things that you can choose. You can choose extent management to be auto-allocate or uniform. Our recommendation is that you choose local management and auto-allocate. But it's important that when you choose auto-allocate, you choose a large initial extent size and a large segment size for extension. If you don't, auto-allocate will start with a small size and then have to grow. As you add more extents or as you add space, it will look at what's being added, and if your extent size is too small, it will make it bigger. Now, it starts quite small, so that's why our recommendation is have a large initial extent size and then have a large auto extend size. So in the example there, we've got a 1500 gig initial extent and we have a 15 gig auto extend. You know, you don't want to be waiting on files to be extended. And there's a couple of wait events. The large initial extent size, if you see wait events for the high watermark or HW there, the NQHW, then you have an idea that your initial extent size may have been too small. And if you see data file init sizes, then that means we're waiting for initialization of the segments. And if you're seeing that too frequently, then think about changing the sizes that you're using there. And also, there's a final recommendation, make sure that you allow unlimited quota on the user that's using that table space to avoid, you know, having to deal with that at each time when additional space gets requested. Okay. Here we have Kermit, right? He's a data ingestion representative. He's trying to get things done as quick as possible, right? We've got things coming in every second, a large batch of things every 30 seconds, every minute, every hour. Right? So we want to get things loaded as quickly as possible. So back to our little shopping analogy, you know, when you're shopping, you don't just put one item in the cart, go and check out, and then go back and get another item. You collect all of the items on your list and then you go and check out once. And the analogy that we're trying to draw here is a comparison between single row inserts and array inserts. Okay. So a single row insert is you add a single row and you issue a commit. And once you issue the commit, everything has to get flushed into the redo logs. Indexes have to be maintained online. All referential integrity constraints have to be maintained as well. And you can expect approximately 500 or up to 500 rows per second per session. Now, with array inserts, what you can do is you can use an API and you can insert multiple rows in one go and then have a single commit. So this reduces read generation, it reduces CPU requirements, it reduces the network round trips, and you can get up to 18,000 rows per second per session from this. Now, obviously you can add more sessions to things, but we'll talk about that in a moment. So committing means that, when you commit, you are persisting changes to the database, right? So issuing a commit after each individual insert generates a lot of redo. It consumes a lot of CPU and IO. We're flushing things to the redo logs. We eventually flush things to disk. We eventually make the changes persistent in the data files. So whichever way you're working, we recommend that you issue a commit after inserting multiple rows. And the example that we've got there is 100 rows. I'm going to talk about some test results later. What we've shown with these tests is that by just accumulating the rows and having a commit per 100, then we can increase the ingestion rate from approximately 500 rows per session to 7,000 rows per session per second per session. Okay, so you can see that there's an easy adjustment you can make there to increase your ingestion rate. Now, we said, you can have multiple sessions acting on the data. If they're working in the same blocks with the database, then you need to have more init trans available. So init trans is something that's set. The default is 2. Work out what's appropriate to allow you to have concurrent inserts within a block. Now, if you're working with disparate blocks, you're working with direct path and things like that, then this is not as important. But if you are working within the same blocks, then having multiple transactions active within there is important. The other thing to consider is that if you're to speed up insert, if you remove table locks, then table level locks, the TM lock, then we don't have to get a shared lock on that table when we're doing the inserts. So you can disable table locking. It means that we're not having to get a shared lock. It speeds things up, but it does mean that any DDL commands can't be run. So you'd have to re-enable table locks if you're going to do a drop, a truncate, an add column, and that type of thing. But it will speed things up significantly. Now, be very careful with this. What we're talking about here is sensor data, and we don't care if we lose some of this data. So if I don't care that it's not, the data is not critical to me, so don't do this for your financial systems. Don't do this for your medical systems. This is, we can set a commit no wait or a commit batch on there. So what it means is that we do an asynchronous commit. So by default, when you issue a commit, we will wait for the data to be pushed to the redo logs before we'll return the success to your committing application. By saying no wait, you are not waiting for the flush. So if your machine crashes before that flush occurs, you'll lose that data, right? And by doing a batch write, we are batching up groups of commits before we're flushing them. So, you can get significant improvement here, but you're sacrificing the ACID properties of your transaction. So be very careful if you are going to use this. So back to our grocery analogy. What about if I'm going to shop for a party? Right? Do I make multiple trips to the grocery store? I've given up my shopping basket and I've got a cart, but my one cart isn't enough. And I've got to fill that cart 3 or 4 times to get all the supplies that I need. Why don't I just make one big trip and go to, Costco? I'm not sure if Costco is where in the country where you're listening from, but if it is, it's just a big, it's a store where you can bulk buy food, clothes, all sorts of stuff. We have it in Australia. It's very big in the US. Right, so what are we saying there? So what we're saying here is we're going to do one big operation, and direct path loads are a representative of that. So direct path loads with or without external tables. So direct path load is preferable over a conventional insert if the data comes in large flat files. So if you've already got the data in a large flat file, we can parse that input data, convert it to the data types that are required for each input field that we're specifying. We can pre-build the database blocks and we push them in above the high water mark. So we're working outside of the table, pre-building the data blocks and pushing them in. Okay, so those data blocks go directly to the data files. They don't go through the buffer cache. They're not going through the SQL engine. So there's significant savings for that. How do we help that? We put the external files where we can access them. So they're on shared storage where we can access them from all rack nodes. Now they also have to be on storage that's going to perform. There's no point having them on if the IO throughput of the storage that we're putting them on has an impact on the load speed, because the fastest that we're going to be able to load is the fastest that we can read the data. All right, so putting them on old remote store or remote storage may not be the best approach. Also think about the data format that you're using. The data, if you don't want to be doing character set conversions. This can be very CPU intensive. It's going to slow things down. The other thing is that if you're using character delimiters for the record terminators and field delimiters, make sure that they're single characters. These are processed a lot faster than multi-character delimiters. Okay. So another way to break up the direct path load is that we can use the partition option. We're going to talk about partitioning a bit more later on, but if you use the partition for approach, then you can prevent acquiring a full table lock on all of the segments. Each partition is treated as a single segment, and so we only have to lock that specified partition as we're doing the load into it. That can have direct benefit to direct path loads. In 19, or actually in 18, we added the Mem Optimization or memory optimization row store for read. And in 19, we added the write capability. So what you do here is you create, you alter your table and enable it for memory optimization for write. And that will then allocate a buffer from the large pool. And then your clients write directly into that in-memory buffer, and then we have a process that will periodically drain that buffer into the table. So it gives you an extremely high throughput because it's deferred writes. In the example here, our temperature sensor is just pushing data as fast as it can into the memory buffers, and it's gradually being drained into the tables. And you can see the performance inserts that we got there on a single X6-2 was 23 million inserts per second. So you can see that this gives a huge benefit. And as I said, there is also a memory optimization for read, which is for essentially reading key value pairs. You have a similar buffer that'll allow you to load into memory and read pairs, key values out of that. This one, if the instance crashes before the data is read out of that buffer, it's lost. So once again, be aware that the ACID properties of the transaction are not met until the data gets into the tables out of these buffers. Okay. Another thing is compression. So Internet of Things data, it's typically ingested once and then it rarely changes. There's a whole lot of duplicate values. Think of sensor data, think of electricity data coming from the one sensor. There's going to be a whole lot of duplicate values around usage. It might be typical values coming in all the time. So what compression does is it reduces the footprint of the data on disk. It improves query performance, and it does, the cost of doing that though is there's increased CPU resources during load. There's a whole lot of different compression options that you have. There's block level compression. There's compression for query, compression for archive, or columnar compression for direct path operations. These are options that you can investigate as to what gives you the best value. Certainly query for archive for older data is important. And then we also have the automatic data optimization, which will automatically compress these based on access of the data over time, where you can then push data out so that it can be archived off onto older to cheaper storage, and because the access requirements are small. Certainly on the ingest, you want things to be fast, so it perhaps should be on better storage. Compress it so that it's expensive storage, so you want to reduce the footprint on there. Reducing the amount that you have to read because the blocks are compressed means that you're able to get more into memory. Everything works better. So compression is your friend. Flexibility. Why does IoT need flexibility? It's because there's new cases all the time. Right, we have to be able to adapt to changes in data formats. We have to be able to manage large volumes of data and quickly analyze them. Developers now typically want to use JSON to deal with this flexibility. It's schemaless and you're not tied to a pre-format. The data defines the format. Well, Oracle supports data. You will have heard of there'll be a number of talks going on over the next few weeks around the converged database story. So JSON, the Oracle database supports JSON. It supports SQL access for JSON, and it runs JSON better than JSON-only databases in most cases. So JSON in the database simplifies app development. We store JSON in table columns and give you SQL access to them. Because it's in the database, all Oracle features like RAC, like replication, like parallel query, like analytics, recognize the JSON format and support it. And we also have added new JSON data types, and I'll talk about them in a moment. They have additional benefit in the IoT concept because they make for faster analysis, and I'll tell you how in a moment. Partitioning is important. So you can partition for any number of reasons, but the two main ones are partition for management and partition for performance. Now, the thing with partitioning is that you're dividing your large table, which is hard to manage, requires full access to read things, into smaller pieces. You're making it easier to manage, and you're improving performance because in most cases, you don't have to access all the pieces. So the best query that you can do is one that you don't have to do. So if you're able to ignore partitions in your queries, then you're not having to access that data at all. So your queries will perform a lot better. Partition pruning is what that refers to. And the thing with partitioning is it's transparent to applications. You just partition your table, and as far as your application is concerned, it's still accessing one big table. But the optimizer is handling, and the partition functions are handling all of the management of the data into the pieces that are needed. So, we can partition by, there's a number of things. We can partition by range, we can hash partition, we can have sub-partitions. There's all sorts of ways that we can partition our data. The example that these next couple of slides is worked on is based on a smart meter reading where they have hourly readings and they keep the data for 2 years, which means that you're going to have over 17,000 partitions, 1 hour of partitions. So breaking this up on a 1 hour range, so each day, each hour, means that we can easily push data in. We're pushing data in at the current hour, and we're pushing the last hour out at the end of our 2 year window. Queries only have to access the data that they need. Now, most queries are going to be, there's going to be two general types of queries. One is going to be, what is my business usage for today, which will be accessing the current partition, or the other could be, what is my business usage, and show me a range of that. So this example, what it did was they sub-partitioned by, they had a hash over the sensors. So each sensor hashed to a particular value, and they had 32 sub-partitions. within that, which meant that if your queries were looking for the readings from a particular sensor, then they only had to go to the subpartition hash that sensor hashed to and read those. So it meant that we could group data in subpartitions. It also helps with compression. We can satisfy the typical queries that we want. And so, you know, if we wanted to look at a 1 day's usage, we only had to look at 24 of the hourly partitions for all of the sensors or for a given sensor. And if we wanted to do a 1 year comparison for a household, we just had to go across the subpartitions that corresponded to those partitions within the window that we're looking at. Okay. So partition pruning, right? We're stripping things out. So by subpartitioning, we can do further pruning of the data. So loading data into a partition table. So if we are running on rack, so we've got our scale out model and it's rack, then we're running partitions in there. If you can affinitize data to a rack instance, then you make life a lot easier. So by having a given partition being loaded on a particular instance, it means that we can spread that loading across each of the rack instances. Now, if you only have 2, it makes it, you know, it's not as big a deal. But if you've got 8, 10, 20 nodes, then you can distribute your loading across all of those nodes and take advantage of the fact that the data blocks are local to a given instance. So in order to affinitize partitions to a specific rack node, we recommend the use of services. Now, we recommend the use of services for a whole lot of other reasons, and you can have many talks on the use of services. But here is another advantage of using services. You can have each service correspond to a given partition and then run that service on a particular instance and therefore distribute your load across those. So here's our example. We've got, I don't know, 4, 5, 6, 10 nodes, whatever it is that we have. And we're splitting up our 32 partitions across our 8-node rack database. And the -R means a preferred instance. So we want our service 1 to run on instance 1, service 2 to run on instance 2, although the numbers are perhaps a bit wrong. And then the -A instance is the available instance. So if there's a failure, we want to move that service to that available instance. So in this example, and in any example that you come up with, you want to distribute your preferred list and your available list equally, so that if you do lose instances or have to take instances down for maintenance while these operations are going on, you get an equal distribution across there, and you're able to service those applications by maintaining some headroom on the other instances. Okay. So real-time analytics. eBay have said, and there was, I can remember a South African insurance company I spoke to, that if they're able to do business analytics work online while they're talking to someone or while someone is performing a transaction with them, they have a much greater chance of success. So eBay will validate credit card details online by doing some analysis across users' activities while you're pressing checkout to pay on eBay. The insurance company that I mentioned, they will analyse all of the risks associated with you and see if your current policy meets the requirements that you have, or whether they should offer you some different offerings. So how can we do that quickly? Well, one way is to use parallel execution. So parallel execution works by breaking up your operations into smaller pieces. So when you connect to the database, you've got a background process that's issuing SQL. If that SQL can be broken up, so we decide that it can be parallelized. Now, there is a cost in breaking it up. So you want to make sure that the cost of breaking up and distributing the work amongst parallel servers that are going to do the work for you doesn't outweigh the cost of just going and getting the data. So it has to be larger amounts of work. So the parallel server, so the query coordinator is your background process. He's coordinating all the work and collating all the results. He farms out the pieces of work to a pool of servers. Now those servers can be running on your local instance, or in a rack environment, they can be running on multiple instances. And they retrieve the data and hand it back to the coordinator, who hands it back to you. So they can do a lot of work remotely and only return the results, or the work can come back and be sorted locally. There's also a whole lot of indexes that can satisfy queries. So these can make queries perform faster, because if you can satisfy them within an index, then you don't have to go to the table to retrieve the information. Now, we offer a whole lot of indexes. The common one is B-tree indexes, but there's bitmap, there's text indexes, there's reverse key indexes, there's function-based indexes, there's all sorts of indexes. Now, indexes are generally smaller than the data. However, there's a cost in maintaining the index. Every row into the table, if you've got an index on there, has to update the index to retrieve things. So there's more CPU, there's more IO on every insert. And the estimate is that CPU use goes up 5 times on conventional inserts for a single index. Redo goes up 6 times, and blocks modified goes up 20 times. So don't have more indexes than you need. Direct path loads are more efficient, but indexes are not maintained on a row-by-row basis. The indexes are built at the end, which means that you may not have all of the data there during the load. How can we address that? Well, you can have partially usable indexes. What that means is that we can use indexes where they exist, and we can do full table scans where they don't. So for example, in this example, we have a local index on a date column for our older archive data, and our current data, which is coming into the hot partition, we can do a full table scan. And you can see that in the Optimize explain plans. So here we're doing a query, it's a union all, we've got a full access of partition 10, and we've got an index range scan on partitions 1 to 9. Okay. I'm running out of time, so I'm going to speed up a bit. Materialized views are important ways of creating real-time data. So most of this sensory data, the individual data themselves, is not as important as anomalies, patterns or anomalies that you can retrieve from that data. So by building materialized views that summarize or aggregate that data, means that you get direct access to the interesting data without having to wade through all of the other data. So you build your materialized views, but you write so you create the materialized views, but you then write your queries to access the tables directly, and the optimizer changes the explain plan to use the materialized view. You don't write queries directly on the materialized view because you want to be able to modify these, you want to be able to change them without impacting the application itself. In-memory model came out in 12.2. It's important. It's a dual format architecture. We just have the row store that we've always had, and we now add a column store, which means that our analysis can go faster. So the analytics and reporting operates a lot better in a column format than it does in the row format. In this way, we maintain both, and the application gets access to both. Whether if it's doing LTP, it uses the row store. If it's doing analytics, it uses the other. And we now have a JSON format, and so there's now in-memory JSON as well. We also have a binary format of JSON called OSIM, which means that a lot of this stuff works faster anyway. So there's now automatic placement of tables into the column store, but you can set them to be in memory if you want, and when you select them, they come in. There's a whole lot of new stuff that's coming in in memory. So when in memory was developed, the focus areas were query performance, mixed workload performance, increasing the capacity of the data store, taking advantage of JSON, which we've done, and automation of the content in the column store. That's all there in 20 now. So we have faster spatial analytics, faster text analytics, SIMD vector instructions provide faster joins. We can do hybrid scans between the row store and the column store now, and automatic population. So you don't have to declare them in memory, although you can. And I'll finish with a few more real-world examples. Garmin. Garmin are growing at around 2 terabytes a month. They have a whole lot of active users where they classify their data based on activity and spatial data. So they have around about 50 terabytes of data. They use local spatial indexes over global spatial indexes, which gave them a 5 times performance benefit. They use a lot of parallelism, and they use pipeline functions to stream data, and they use services and instance caging to allow resource manager to prioritize their work functions. RWE is Germany's electricity and gas provider, one of the top providers in Europe. Around about 6 million households on electricity, 1.5 million households on gas. They use smart meters. They gather their data from the smart meters, and they ingest around 2.4 billion reads a day, and that gives them the capability of running a lot of sophisticated assessment so that they can avoid peaks and offer new tariffs. And Canon now, as one of their services, is managing multifunction printers. They have over 1 million multifunction printers in 100 countries. They also offer a whole lot of document services and full printing services for customers, but they are using an Oracle database behind that to do all the monitoring of these printers everywhere. All right, and I'm going to stop there, and I'll see if there's anything in the chat. There's nothing in the chat. We still have a few minutes left, I think. So yes, I will show you. Yep.
No, it's all good. And then just to give everybody just the chance, if you've got any questions, please feel free to add it in the Q&A box at the bottom. You'll see it there on the Zoom tab. So if you've got any questions, please feel free to add it there.
So while we're waiting for questions to come in, you will get this presentation. There is a whole lot of work that we've done, not just with customers, but we've run a whole lot of internal testing as well to validate a lot of the statements that I've made. We ran a whole lot of tests with a full rack of X6-2 with 12.2. We need to update this for 19. We had a table of 8 columns, 7 numeric columns, 1 date column. We had 32 partitions. We used a C program, and we played around with array inserts, batch inserts, commit frequency, local indexes and global indexes, and these are the results that we found from that. But there's a write-up of all of this that you can get. So you can see that, you know, we got up to 20 million rows per second where we were doing array inserts with 1 local index and committing every 100 rows. Now that's spread across the 8 racks, right? 2.5 million rows per second per rack, per node. Right. But you can see that there's a significant difference can be had by committing in batches of rows, by managing your index strategy, by partitioning your data, right? And graphically that looks, where's my graph gone? Graphically that looks like that, right? And so in summary, it's that scalability, flexibility, real-time analytics. Now, hopefully I've convinced you that the Oracle database has all of the capabilities and characteristics that are needed to manage Internet of Things workloads. And as we said before, you can ask questions now, you can ask questions later. We'll be looking for this. You can also contact me directly. My email address is floating around on the OUC website. So,
cool.
So if you have any questions, please do that.
Yeah, there's a couple there in the Q&A box. I'm not sure if you want to have a quick look at those.
Is there? Okay. Oh, there is too. Okay. Q&A. Regarding in-memory, what's the best choice for selecting it before putting it to use? So, it's going to for in-memory, it's going to put data into a column store. So if your data is best represented with that, then if you're doing analytics on it, then put your driving tables into the column store and then go from there. Now with 20C, and I don't think it's into 19, but it's in 20, is the automatic population. So we will analyse the results that are coming through, and we will populate tables directly if we think that they will benefit from being in the column store. Otherwise, do that. Second question, will IoT transactions generate high volume of archive logs? Yes. Yes. So sizing your redo logs is important. You want to look at your peak throughput so that you're not doing too many log switches. So you want to look at the size of redo logs and size them appropriately, that you're not doing too frequent log switching. Otherwise, things slow down on the log switch. You want to put them on fast storage too. So you want to put them locally. They have to be local, but you want to put them on something fast, solid state disk, flash, whatever. Right? Don't forget to use auto commit. Yes, the only thing with auto commit is it can. So Chris Jones says don't forget to use auto commit when using array inserts. So don't forget to use auto commit. So that is important to get that through there. Thanks, Chris. Any test cases shared for these implementations? Yes, there is a write-up for this. It is referenced in when you get the presentation. There's a link to the write-up for this, which will it will link you to the customers or most of the customers that I mentioned, and give you some information on what they're doing. But it will also link you to the test case that I talked about. And an anonymous attendee has said Geelong by 6 goals tomorrow. For those in Australia, they know what I mean. Yeah, I'm going to go for the Cats. So tomorrow, for anyone who doesn't know, is it's the grand final of the Australian Football League. For anyone in America that's listening to this recorded, it's a Super Bowl equivalent. And Geelong and Richmond, which are two Melbourne teams, are playing in Brisbane tomorrow. And yeah, I think I'll support Geelong.
Cool. Thank you so much. Thank you everybody for joining the session. That was really jam-packed, full of a lot of information. Just want to highlight again what we said in the beginning, that these sessions are being recorded and they will be uploaded, and they'll be available for 2 weeks after the session has been uploaded for you to view and everything. Also, please feel free to register for other sessions. There's still a lot of sessions available that's scheduled over the next few days. So please do have a look at those. And yeah, feel free to contact the speakers and have a discussion with them. Thank you so much, Troy, and thank you so much, everybody, for joining this session. And hope you have a great week.
Thank you.